Okay, in this video, we're going to look at how to tackle a sequential move game. Specifically, we're going to look at how to figure out the expected value and how to figure out if a payoff changes, can we make the game more fair? And we're going to specify one particular player. So if you need any help with either expected value or changing a certain payoff, hopefully this video is really helpful. So first things first is we're going to walk through the problem, identify some key pieces of information, and tackle it step by step. So feel free to move ahead in the video, whatever you really need. So a two-player sequential move game, so we're talking about one move and then the next move, uses a standard deck of cards. Okay, so that's good to know that we're dealing with a standard deck. Remember that there are 52 cards in a deck. Remember that goes from 2 to 10 in the numbers, Jack, Queen, King, Ace. There's 4 of each kind of card because there are 4 suits in the deck, so just all helpful information to know. All right, and then there are the following rules. Player 1 chooses 2 cards, so even though they're choosing 2 cards at the same time, we already said that it's a sequential move game, so we can treat it as if it was one card, then another. So even though it says 2 cards, and even if you were to take them 2 cards at the same time, we're still going to treat it like it was a sequential move, one move and then the next. All right, they say that for every face card drawn, so a Jack, Queen, or King, Player 2 owes Player 1 $5. Well, we know now it's a standard deck, so there are 4 Jacks, 4 Queens, and 4 Kings in the deck. And now we have a payout of $5 for every time a face card comes. And then if no face card is drawn in those 2 draws, Player 1 owes Player 2 $3. So in this case here, we're talking about a -3 payoff for Player 1. All right, so we're going to find the expected value first and talk about what it represents in the context of the problem. And in order to find expected value, remember that we need 2 things. We need payoffs and we need probability. So we want to know what is the likelihood of a certain payoff to happen. Well, first, if we want to find these probabilities, we have to do a probability tree. So we're going to do that now. And we note that our probability tree is concerning ourselves with the face cards. We're concerned about if we get a face card or not. So we have 2 draws, the first draw and then the second draw. And again, even though they're getting pulled at the same time, it's a sequential move game, so we treat it as look at the first draw. So we take 1 card, see what happens, and then we take another card and we see what happens. So first draw can either be 2 things. It can either be a face card or not a face card. Those are the 2 options that we're really concerned with here because we're keeping track of how many faces Player 1 draws. Well, in there are 52 cards in the deck. We said it was a standard deck. And we saw that there are 4 Jacks, 4 Queens, and 4 Kings, so there are 12 face cards total. Because any one of those, a Jack, Queen, or King, could be a face card that could be pulled, and that would mean that Player 1 gains $5 from that. Similarly, that means that everything else in the deck is not a face card. So all the numbers and the aces, that means there are 40 non-face cards left. 52 cards total. Pull away the 12 face cards. Everything else is not a face card. So again, a 2 through 10 or an ace. Okay. Now we do the second leg. So we take another card. And we're just keeping track of how many faces or not faces we get. But the thing that's going to be different here, face, no face, face, no face. The difference in this second draw is that we're assuming we've already pulled 1 card from the deck. So instead of having 52 cards now, we've already pulled a card. So regardless of what happens on the first one, there's 51 cards available. Now, the numerators are going to change depending upon what happened on the first draw. So, for instance, on this far left side, if I drew a face card first, and I want to see what is the likelihood I draw another face card, where Player 1 draws another face card, well, there are 12 face cards that were there. We took 1 of them away, so now there are only 11 face cards left. Similarly, still on that left side, if we drew a face card first, that means that all 40 non-face cards remain, so all of them are still in play. So the probability of getting a non-face card after getting a face card is 40 over 51. Okay, by that same logic, if we keep going to the right, We drew a non-face card on the first draw, which means that all 12 face cards still remain. And finally, on the very last option, I drew something that wasn't a face card on the first draw. So of those 40 non-face cards, one of them's gone, leaving us with 39 left. So one of the non-face cards is drawn. Okay, so now let's look at all of the probabilities, or let's look at the payoffs, and look at the probability. So the payoff for player one. All right, well, in the first path, we're going path by path here, and I'm going to try and highlight this to show what's going on. If we drew a face card on the first draw and a face card on the second draw, that means that player one found two face cards. They get $5. They get $5 for every face card. So that means in this situation, they're getting a $10 payoff, two face cards. The probability of that happening is the product of the probabilities along the pathway. So that means the probability of getting two face cards is 12 over 52 times 11 over 51. And we can actually take that same approach for every single one of these other pathways. And I'll do all the multiplication at the end. So we're just going to hang tight for now. Okay, but let's keep going down the pathways. So let's say that we draw a face card on the first one. Whoops, sorry, we're going to keep my paths going. I want to try and get these different highlighted colors going so you can really see what's going on here. Okay, we get a face card on the first draw, and then a non-face card on the second draw. So we got one face card in that sense, so that means we got $5 of a payoff because we drew one face card. And then the probability of that is going to be the product of those probabilities along the way, 12 over 52 times 40 over 51. And then just so that we're staying consistent, and I'm actually going to save us some space, I'm going to do the multiplication now. So that's 0.05, that's 0.181. Okay, the next one, probability of not getting a face card and then a face card, should be the exact same as the other one. It's a $5 payoff because we're only getting one face card. And regardless of whether we get it first or second, it's still going to be the same probability. You can multiply those numbers out if you want to, but it's going to be the same thing. And then finally, if we look at the likelihood of not getting a face card and then not getting a face card, and I'll keep all these consistent with the green and the green. That's the green, green. And that's a yellow probability because that's two face cards. Okay. Not getting a single face card. Well, we said in the rules that if no face card is drawn, player one owes player two $3. So that's a -3 payoff. And the probability of that one is, again, the product of the probabilities along the branches. So 40 over 52 times 39 over 51. Which we get a decimal point of 0.588. And you'll notice that you want to try and keep it to two decimal places or three decimal places if you can. I only rounded to 0.05 in that first one because it's like 0.49, something that just rounds up really easily. Okay. So we've got all of our payoffs, we've got all of our probabilities. Our expected value formula is the product of those things and then the summation of the products of each one of those events. So it's the payoff of the first event times the probability of the first event, plus the payoff of the second event times the probability of the second event. And we go all the way down to the payoff of the nth event, however many events you want to have, times the probability of that event. So in this case here, we have a $10 payoff times a probability of 0.05. Plus a $5 payoff times a probability of 0.181, plus a $5 payoff times a probability of 0.181, plus a $3 loss, which is going to happen about 0.588, so about 58% of the time, 59% of the time. Okay. We multiply all these together, so that's 0.5 plus 0.905 plus 0.905 minus 1.764. And if we add all of these things up, we get an expected value of 0.55 rounded to two decimal places. Okay. That's my expected value. And in the context of the problem, that means that player one can expect to gain 55 cents per game. So notice that player 1 will never actually gain 55 cents in a certain circumstance, but if they were to play this game forever and ever in the long term, they can expect to gain 55 cents per game. So if they were to play 100 games, they can expect to gain $55 by the end of that. Now, it's an approximation. It's not a guarantee here, but we can use this value to then say, you know what, player 1 has some kind of advantage here. The payoff is worth the risk because you see probability-wise, all of these probabilities are lower than the probability that a player will lose in a given game. So the payoffs are almost worth the risk for player 1 in the long term in this game. That's really what that means. So that then leads us to our second question, because if we were to change player 1's payoff, we could make the game more fair. Because if you're player 2, you might say, you know what, yeah, I could win on one given game, but if I were to play this game forever, I'm not going to want to play this because in the long run, I'm going to lose 55 cents a game. So if I play 100 games, you're going to lose $55. That's not a great deal. So the question becomes, how can we change player 1's payoff so that the game is more fair? And when we say more fair, we're really saying that we want an expected value equal to 0, which means that in the long run, no player is winning or losing more than another player. So the question becomes, how do we change player 1's payoff to keep this more fair? So we're going to let X be defined as player 1, their new payoff per face card. Sorry, we're talking about face cards. Per face card. So we're wondering, what do we have to actually change? Instead of $5, what do we change the amount of money that player 1 will get every time they get a face card so that we get an expected value equal to 0 so that this game is fair? We can't change the probability, so this formula that we were working with, those probabilities are going to stay the same. So we're going to let's write out first the sort of the old expected value. And we said that was 10 times 0.05 plus 5 times 0.181 plus 5 times 0.181 minus 3 times 0.588. Well, if we want expected value equal to 0, what we're doing is we're changing player 1's payoff. So we see that there was a $5 payoff, a $5 payoff, and a $10 payoff, and all of those come about from when player 1 draws a face card. So instead of getting $5, they're going to get X dollars for every face card drawn. In this situation where no face card is drawn, there is no X that's necessary there because no face card was drawn, so they didn't get anything. And in this first situation, they drew 2 face cards, so the amount of money that they're getting there is actually 2 times this value. So we're going to call that 2X because, again, they drew 2 face cards. 2 face cards were drawn here. And now this just becomes an algebra problem. So I'm going to add, so first things first, let's multiply everything together. So this is going to become, let me keep everything consistent. So 0 is equal to, I'm going to multiply 2 times 0.05. So this is 0.1x plus, and then I'm going to move the variable to the end just because I'm more comfortable with it, plus 181x plus 0.181x minus 3 times 0.588. We've already seen is that 1.764. Okay. And now we're just going to solve for x here. So this becomes 0 equals, we can combine like terms, so add up the coefficients. Excuse me. So that's going to be 0 equals 0.462x minus 1.764. And we're going to solve for x, so we're going to get everything that's not an x over to the other side, so 1.764. So this is 1.764 is equal to 0.462x divided by 0.462 divided by 0.462, undo multiplication by doing division, and we get an X value equal to 3.82. So this tells us that if we change player one's payoff to $3.82 instead of the $5 as originally done, expected value is going to equal 0, and then both players don't have an advantage long term. So again, this won't happen on a given game. This is in the long run. So in a long run, player one might have an advantage if they maybe play 5 in a row and they win all 5 or something like that. Like, there still could be a probabilistic advantage, like something could happen more likely than something else. But now we're saying that if the payoff is this 382 for player one, it would be a little bit more fair. Excuse me. You'll also notice that we did this for player one. We could have easily done this for player two, and we could have made this X and changed the payoff for player two. Maybe player two makes a little more money if no face card comes by. We could have easily done it there too, and then left all the other numbers. So identifying what your variable is early on is important, because we want to see first off what's the problem asking for, and then seeing where to plug in the variable appropriately. So hopefully this is a helpful summary of how to find not only expected value, but then how to find a change in payoff so that it makes the game a bit more fair.